Okay, so these are notes on the frictional force. So to start off, let's look at the symbols we're going to need to build up to the equation for frictional force. So the first one is the normal force. So we'll need to know what the normal force is. So the symbol for that is F with the sub notation of N. You might also see a lowercase n as a notation, but I'm going to stick here with the sub notation N. And then we have two types of frictional forces. We have the kinetic frictional force. So I'm going to symbolize kinetic frictional force with an F sub K, and the static frictional force, which again I'm symbolizing with a script F sub S. We also have the applied force. So this is a force that is applied to the object, and we have the weight of the object, or the force due to gravity, and I'm going to represent that as mg. Okay, so let's jump into the definition of frictional forces. So for a frictional force, it's a force that opposes the motion of an object, or the force that opposes the applied force if the object's in equilibrium. So let's break that down. So the force that opposes the motion of an object. So if we have an object being pushed on a surface, and that surface has friction, then we're going to represent the frictional force as being opposite of the velocity. And in this case, since we have a frictional force in the x direction that is opposing the velocity, we know our acceleration must be to the left. So when we have an acceleration to the left and a velocity to the right, this object shows that we are slowing down. So a quick note, if we look at the normal force is the same size as the weight or the gravitational force. We'll talk about this more in a second. So this is the frictional force opposing motion. Well, we can also have a static frictional force when the velocity is equal to 0. So this object is stationary. And this would be my force applied. And I'm pushing on this to the right. So the frictional force is going to the left. It opposes the applied force. And this is in equilibrium, so the forces cancel out. So this force is equal and opposite that force. So there is no motion here if this is stationary. And we know it's stationary because it's a static frictional force. If we come down here now to a kinetic frictional force, well, kinetic means moving. So now I have a velocity, and we can put the velocity going to the right, and the acceleration would be 0 because if it's in equilibrium, then all of these forces, the forces in the x direction will cancel out, and the forces in the y direction will cancel out. So we have no net force. And if we have no net force, we can either have the object as moving at a constant velocity, or we can have the object as being stationary. So as an important note, we know that the frictional force is always parallel to the surface. So when I'm drawing in my frictional forces, the frictional force will be parallel to the surface force. And you can see that in all these cases. Alright, so before we lead up to the definition of frictional force in equation form, we have to know a few things about the normal force. So the normal force, well, in mathematics and physics, normal means perpendicular. So the normal force is always perpendicular to the surface. And if we ask what is the normal force, well, we get the normal force from Newton's third law. Since an object applies a force on the surface, usually due to the gravitational force or its weight, the surface is going to apply an equal and opposite force onto the object. So if we look at a free body diagram down here, we have a free body diagram, so it's showing the forces on the object. And this object's in equilibrium, and I can tell that because these force vectors are equal in size. So this is an object just sitting on a surface. So it could be just sitting there, or it could be moving with a constant velocity as well. So either one of those scenarios would work for this. So in this case, so we have the normal force is perpendicular to the surface, and we have the weight of the object is going down. So if we look at this for the normal force on a flat horizontal surface, we see that the normal force just goes straight up and it opposes the weight. But in this case, if we have a ramp, well, now the normal force, if it's still going to be perpendicular to the surface, then since the surface is at an angle, we call that theta, the frictional force is also going to be at an angle of theta. And the weight, mg is always down, directly down to the center of Earth. So mg is always going to be down. Okay, so let's look at, let's go back to this one, so the free body diagram. So if I want to solve for my normal force, well, my normal force is, in this case, equal to my weight. And you can see that by summing the forces in the y direction. Since it's up and down, we're going to sum them in the y direction. And we're going to set it equal to mass times acceleration. This is Newton's second law. But since I'm not accelerating, I'm going to say that the mass times acceleration is 0. So when I sum my forces, I have a positive normal force. I have a negative weight or gravitational force. If we're saying up is positive and down is negative. So when I isolate the normal force, in this case, it is equal to the weight of the object. Let's come over here and look at this scenario now. So if we have this object here, this object cannot be in equilibrium. It can't be stationary. Because we have a force that's pulling up to the right and we have a force pulling down, there is no force pulling to the left. So in this case, the crate will be accelerating down the ramp. So let's look at that. So we know that it has to be accelerating down the ramp. And we have our weight pulling it down. And our normal force now, here's where, again, it's perpendicular to the surface, so it's at this angle. Now, here's the trick that we did in a couple of our problems, but makes problems a lot easier to solve. Since here we have our acceleration at an angle going down the ramp, and we have our normal force at an angle, then if we shift this, we can make both of these forces, or this force and this acceleration, parallel to the surface. And if we shift it, then we would have the weight or the gravitational force at an angle, but it makes it much easier to just have one force at an angle and have the acceleration not be at an angle. So in this scenario, it's much easier to just do the shift and to solve. In this case, we're isolating the normal force. So by doing the shift, if I shift this down, and maybe you can see this, what's going on. I'm shifting this whole thing down to make it horizontal. And when I do that, when I shift it down, I'm shifting, you can see my weight is now going to the right. So here my weight or my gravitational force is going to the right, and whatever this angle was shifted down, well, now that angle becomes the same angle but with the vertical now, not with the horizontal. So now if I'm looking at this scenario here, so let's just look at this scenario, and I'm trying to find out what my normal force is, then I can use Newton's second law and I can sum my forces in the y direction and set it equal to 0. And I can set it equal to 0 because I know that the box is not coming off of the ramp and the box is not going below the ramp. So in the y direction, these have to be these have to be equal to each other. So since F of n is just going straight up, I'm going to say my normal force is vertical. So it's going up, I'm going to give it a positive. And my mg, I only want the component that is in the vertical in the y direction. So what I'm going to do is I'm going to find out what is this component right here of the force of gravity. So to find this component, well, this is my adjacent side to this angle. So when I come down here and I find out the component, I'm going to use cosine of the angle because it is the adjacent side. Now when I isolate my normal force, I'm going to move this mg cosine of theta by adding cosine of theta to both sides. And I come up with this expression or equation for the normal force. Okay, so let's look now at what actually causes the frictional force. So this is some concept of, well, if we look at why do we have these forces of friction, and the reason why we have the force of friction is if we could make this look at the surfaces in detail on a really small scale, then nothing is absolutely smooth. There's always going to be ridges to something that is on the very small scale. You can't have perfectly smooth. So on one of the surface you'll have these jagged ridges, and on the other surface you have a jagged ridge. And if it's static, you can think of those ridges have kind of slotted down into each other and they're preventing the movement. So if you look right here, that piece of the top object and the piece of the surface are going to bump into each other, which gives it that frictional force. So this static frictional force, the velocity is equal to 0. But now if we have a velocity greater than 0, well, now we have a object that's moving, and in this case you can think of the object kind of rises above these ridges here, and it's still bumping into them, but they're not as locked down in place. So the analogy that I have is, if you think about you're riding a bike on a rocky road, it's harder to start pedaling from rest because you've settled down into the rocks. But once you start moving, you can more easily ride on the bumps and the rocks because you ride up above the surface and you're not going deep down into the slots. So the frictional force, the static frictional force, is always going to be greater than the kinetic frictional force. So in order to analyze the surfaces now, we need to look at the coefficients of friction. So the coefficient of friction is a ratio of the frictional force to the normal force. So this allows us to solve for the coefficient of friction. This coefficient of friction symbol is a Greek letter mu. It looks like a U, but we'll say in class that this is mu. And I have a mu sub s, so I have a coefficient for my static frictional force, and I have a coefficient for my kinetic. So when I'm not moving and when I'm moving. And so this is an important note that the coefficients only depend on what the two surfaces are made of. There's nothing else that determines what the coefficient is. And this might seem counterintuitive. You might think that surface area, if you have a greater surface area, then mu increases, but this is not the case. So you would think that if you had two objects, let's say a small wood block on a surface, so let's say cement, if you make that wood block, if you make that wood block a bigger surface area, you might think that the coefficient increases, but that is not the case. So the coefficient only depends on the two surfaces that they're made of. So the coefficient, since it only depends on the surfaces, there's a unique static and kinetic coefficient for any two surfaces. So let's look down here at a table of the coefficients. So a coefficient of static friction for steel and steel. Through experiment, we can measure this and give a coefficient of saying that this one is 0.74. And we get this just from the ratio that we showed above. So this is the static frictional force, and if you notice the static coefficient, and you can notice that the static coefficient is always greater than the kinetic coefficient. And we look at these and we see that that's the case. And that's the case because the static frictional force is always greater than the kinetic frictional force. So the coefficient only depends on the material. If we look wood on wood, the coefficient has a range from 0.25 to 0.05, depending on what wood, and the kinetic friction, now it drops to be 0.2. Let's look at one more. Let's look at one that has a low static friction. So if we look at ice on ice, well, in that case we have, well, let's look at this one. So one that has a lower coefficient of friction. So let's look at this one. So synovial joints in humans. So you would imagine that your joints would have a very small frictional force. And this shows that this frictional force is 0.01. And over here, the kinetic friction is even lower, so 0.003. All right, let's move on to looking at the equations. So what are the actual equations for our frictional force? So for the kinetic frictional force, so remember that we said that U mu sub k, the coefficient, was equal to the ratio of my frictional force to my normal force. So this is the ratio, and we find that through using this equation. So this equation says that my frictional force is equal to my coefficient of kinetic friction times my normal force. There is nowhere in here that calculates in area, so surface area is not in this equation. But what is in this equation? If we look at the normal force, if we increase the normal force and keep the coefficient's going to stay the same. If I increase the normal force, well, what that does is that increases the frictional force. So I'm drawing these big symbols to represent that the frictional force increases when you increase the normal force. And the same thing would happen on opposite that. If I lower my normal force, then I'm going to lower my frictional force. So this says if you have a, let's say, brick on concrete, well, brick on concrete, I'm going to have a frictional force that is related to the normal force. So in this case, let's say F of n is equal to mg, and that gives me a certain frictional force. Well, if I increase the normal force, and I would do that in this case by increasing mg, so if I increase the normal force, this in turn increases my frictional force, which is what you would think, that if you have a heavier object on two surfaces, then the frictional force will increase as well. Alright, now there's a little bit of explaining that we have to do for this one. So this says that the static frictional force is less than or equal to the coefficient of static friction times the normal force. So if you think about that, let's do an example where you have a man or a woman pushing on a refrigerator. Well, as the man is pushing on the refrigerator, so if he's pushing in this direction, the static force, if the velocity is 0, then the frictional force has to be equal and opposite, exactly opposite of what the applied force is. So if you're pushing with an applied force this direction, if it's not moving, then the static force is opposing that. But now let's say that you increase your applied force. Well, now your frictional force has to also increase until you get to a point where finally you break the static friction and then the object starts to move. So once you have applied enough force, your frictional force is going to drop. It's not letting me do that. So your frictional force then is going to drop and you'll end up with a movement. So in that case, now your velocity is not equal to 0. You have some kind of velocity. And now your applied force, you are now in motion and you've switched from static to kinetic. And if we look at the graph of that, so the graph of F versus the applied force, so this shows exactly that of the scenario of pushing a refrigerator, that as you push, as your applied force increases, the static force, or the frictional force, also increases. And it increases all the way up until you get to this point right here. And that at that point, that's your static frictional max. That's the max friction that the object can apply before it starts moving. So your Fs max is equal to your coefficient of static friction times the normal force. So this is the max friction, static friction, that the object can apply. And then here it shows once you have broken that static frictional max, that the object comes down here to become kinetic friction. And so that kinetic friction, what this shows is as you increase your applied force, the frictional force doesn't increase anymore. It just remains the same. So it is remaining the same even as you're pushing harder and harder and harder. Well, the frictional force equals out and it stays the same no matter how hard you push. So the static frictional force is equal to the applied force. So right here, static friction is equal to the applied force until it hits the max, and that the friction, that the object can withstand with the friction. Then it starts to move, and the frictional force drops to the kinetic frictional force. Now this is true. This is a true statement for if you're being general. So in our physics, we're generalizing this. So it's important to note that this might not hold true for certain objects and certain experiments, but it gives us a general relationship that shows us that the frictional force remains constant no matter what applied force you have on the object. Okay, so we will jump into some example problems of this. But hopefully for your notes, you have written this and have an understanding of what this equation or these equations state.